Here we go, board lecture. Okay. So, the key players. And always have in mind, you know, the credit card example. So let's begin with the application. So you have a person applies, so applicant. Well, you know, we can't capture everything about an applicant. So there are certain things that we capture about the applicant. You know, salary, age, debt, and so on. Okay, so the applicant's attributes, the applicant's features. Well, you know, what are these? Well, we can just represent them by a bunch of numbers. So if you have 10 such things that you collect, then you'll represent it by 10 numbers or a vector of size 10. So we'll represent the applicant's attributes and we will generically call it the input, X. Okay. Now, you know, we don't need to restrict ourselves to exactly 10 features. So generically we will say that X belongs to a d-dimensional vector space, in which case there are d attributes that have been collected. Okay. Now, what's the goal? The goal is to say yes or no in this particular case. Okay, so should you approve for credit or not? Okay. Well, this decision we're going to call the output. Okay, now we could encode the output as yes or no, but it's generally more convenient to exclusively live with numbers. And so an equivalent way of encoding yes or no is just to say that you're supposed to say +1 for yes or -1 for no. Okay. So the output is either +1 or -1. And this output we will generically call y. So in this case, the output belongs to a finite set, plus or minus 1. This is called a classification output because you're classifying the input vector x, i.e. you're classifying the applicant into one of two categories, yes or no. Now, you know, as we progress, we will see that you can have a very different types of problems where y may be more than one class. So for example, in the digit recognition problem that I showed you, which will be the one we use throughout the class, the possible outputs are 0, 1, 2, 3, up to 9. So there are 9 classes. Okay. It's possible that instead of telling me yes or no for credit, it's possible that you say, don't tell me yes or no for credit, tell me the credit level. Well, in that case, the output is any positive real number. Okay. So whatever the output is, it belongs to some space. Okay. In this particular case, plus or minus 1. So generically, what you are asked to say for a particular input x, we're going to call the output y. Okay. Now, remember that, if we're going to attempt to do machine learning, we assume there's a relationship, a pattern exists. Okay, so that's the first non-trivial assumption. Okay. So this pattern, now there are many different forms that this pattern can take. Okay, but to simplify the discussion, we're going to assume that the pattern that we say hypothetically exists, okay, or that we assume exists, is going to take the form of a function. Okay, and we call that function the target function. Target function. So in other words, there's a function which tells you what's the correct y for any particular x. So the target function f, maps x to y. Or we could say that y equals f of x. Okay. Now let's state the most fundamental ingredient in the machine learning problem. So remember, the class motto, a pattern exists, we don't know it. So the pattern exists, we don't know it. What does that mean? That means that this target function f is unknown. Unknown. Okay. Do you really mean unknown? I mean unknown. Okay, now, of course, the problem gets a little bit easier if I tell you something about the target function. I tell you this, or I tell you that, or I tell you this. But that just restricts the target function to some other set, and within that set it's completely unknown. Okay, but as a most basic assumption, we must maintain that the target function is unknown. Okay? And if you try to think about it, try to think about what kind of a function relates an absolutely generic picture and outputs plus or minus 1 if there's a tree. It's probably this very complicated, bizarre target function, okay, which is truly unknown. It could be almost anything. Okay. Now, this is one of the things that makes machine learning very hard. But maintaining that assumption is one of the things that's going to allow whatever theory we develop to be absolutely broadly applicable. Okay. So if we can develop a theory of learning that applies to this situation where the target function is absolutely unknown, then it's absolutely general. Okay. All right. So remember, a pattern exists. We don't know it. Okay. And if this thing exists, if this target function f exists and we don't know it, well then how are we going to in any way whatsoever figure it out, because it's completely unknown, and that's where the data comes in. So we have data. Okay. And so let's pin down exactly what data is. So we're going to assume that even though we don't know f, we're going to have data which consists of examples of f in action. So the data consists of examples of f in action. So what does that mean? That means, just like in the credit application scenario, when you think about what's the data, you have a whole bunch of applications. Well, a whole bunch of applications corresponds to a whole bunch of inputs. So you have a whole bunch of inputs, x1, x2, x3, xn. You have a whole bunch of inputs. And somehow, for those inputs, you have managed to obtain f. In other words, should you have approved credit or not, in the case of credit application. So somehow you have managed to obtain f, which means that you have obtained y1, y2, y3, up to yn, where yi is equal to f of xi. Somehow. Now, this collection of examples is what we call the data. We'll call this the data set, and sometimes we will say it's a data set of size n. So get used to this notation because it's going to be used for the whole semester, okay, throughout the whole course. X is the input, y is the output, the unknown target function is f, the data is x1, y1, x2, y2, x3, y3, and so on up to xn, yn, where each y is f applied on the corresponding x. Now you might ask, well, how did I get this data? Very good question. Okay. Now, for the moment, don't care. That's not the content of the machine learning. Okay. The assumption here is that we have this data. Now, as we develop the theory, we're going to see that as we develop the theory and ask the question, can we learn? And then we say, oops, it doesn't look like we can learn, but then we come back and say, oh, but maybe it is possible to learn, and then we build the theory and so on and so forth. That's going to dictate some properties that the data set should have. Okay. So, modulo those properties that the data set should have, it's not my business as the machine learner to know how you got the data. You just need to give me the data satisfying the theoretical properties that I need. Okay, one of those properties is this most fundamental property that y equals f of x. Now we'll be able to relax this to the situation where we say y is approximately f of x. In other words, it's f of x plus some noise. That's not going to be a problem. But fundamentally, the y's are related to the x's through this unknown target function f. Okay. And so the data, even though we don't know f, the data is indirectly giving us some information about f. Okay. And so we're going to try to reverse engineer f. Now, we may not get exactly f, okay? But what matters is whatever we get, we're going to use in the future. So it's not okay. You might say, well, that's very disappointing, Malik. You're saying that the data, which is a fundamental ingredient into the machine learning problem, and then you're not telling us how to get the data. Well, that's because I'm focusing more on the machine learning problem, but yes, I'm not going to tell you how to get the data. Nevertheless, it is very important how the data was obtained, and that it must satisfy the theoretical properties that we need of the data. Now, let me give you that having been said, even though that's not the focus, let me give you an example of how we could get the data in the credit application. Well, we have all these people who applied, okay? And let's say we take all the people we gave credit to, so that's these n people. We gave credit to them. Some of those people defaulted, so these are the defaults. And some of those people did not default, so they paid off. Okay. Well, in this situation, we could say, well, this was a bad idea, so you should not have given these people credit. So the answer should have been no. In other words, we can sort of infer that f of x for all these defaults, we can infer that f of x should have been -1. So we would put all these y's to -1. The x's exist by default in the bank. Okay, and we should set all these y's to +1 because they all paid off, which means that it was a good idea to give them credit. So here's an example where we were able to extract a data set which represents this target function for the particular machine learning problem of credit approval. If you think very carefully, and I don't want to get into it now, but if you think very carefully, you'll see that there might be something a little bit fishy about this data set, the way I've constructed it, and we'll deal with that later. Okay. But there's an example of how we could create the data set. Okay. So this is the setup where we say that machine learning is relevant. A pattern exists, f, we don't know it, f is unknown, we have data. Okay. Data set x1 to xn. So let's put this in some kind of a box. Okay, so you have an unknown target function. F of x. Okay. And this unknown target function, we're going to use it. We don't explicitly use it, but we indirectly use it. For example, in this in this credit card approval. So we indirectly use it, or we basically assume it has been used in order to get my data set, which is yi equals f of xi. Now I don't see f, but what I see is the result of applying f to xi. I have a data set which consists of pairs xi, yi. So we have x1, y1, x2, y2, and so on, x big N, y big N. The big N is the number of data points. Okay, good. So in some sense, this picture summarizes that entire discussion where implicitly we have this x, the input, we have the y, the desired output. Okay, we have a data set which is examples of f in action. Okay, good. Okay, let me erase, since this is all now contained in that picture. Let's talk about the learning. So, learning. What do I mean by let's talk about the learning? What's all this? This is just the setup that says machine learning is a plausible, is a feasible approach to reverse engineering F. Okay. And the process that actually does that reverse engineering is what we're calling learning. Okay. So, let's put it in quotes, getting F. Somehow. Now, how do we get F? Well, you know, if we could get F exactly from the data, that would, in almost any case, be a miracle. So in general, we're going to assume that we're not going to produce F. Okay? So whatever learning means, the result of the learning is going to be an approximation to F. Now, that's without loss of generality. That doesn't exclude the possibility of producing F. So we will say that the result of learning is an approximation to F. And we will call it G. Okay, so G is the output of learning. So G is a beast of the same form as F. In other words, G maps X to Y. Okay. Much the same way as F maps X to Y. So F and G are functions from the same input X to output space Y. So if we're talking about classification, F takes X and produces plus or minus 1. G takes X and produces plus or minus 1. Classification is the credit application. Okay. So we need to sort of decide, what does it mean to have learned? Okay. And here we are exactly pinning down the learning problem. Okay, so what does it mean to have learned? Okay. So let me throw out a couple of possibilities. Possibility 1. Well, you know, since we have a data set, okay, and we know that, you know, for each of the x's in our data set, y is the corresponding x, f of x. So we know that yi is equal to f of xi. So wouldn't it be nice if yi is also equal to g of xi? So let's see, what does that mean? What that means is that g is able to reproduce exactly f on the data set. And why don't you pause the video for a moment and think to yourself, you know, is that worth anything to me? Okay, so if you pause the video, great. If you didn't, then I'm here just for the ride. So here's the news flash. Why would I go through all of this hassle if the only thing that comes out of it is that I can reproduce on the x's that are in the data set the y's that are also in the data set? What am I going to use this g for? It's of no use. I already knew these y values. I don't need g to tell me those y values. I've wasted my time. So in some sense, yes, this will be nice, but is of no use to me. Okay, now let's think back to the 5-year-old telling me which pictures had trees. Okay. Those pictures the 5-year-old never saw, and now I'm impressed because, wow, you never saw these pictures and you figured out which ones had trees. Let's talk about Netflix. Netflix doesn't care about predicting the rating of a movie that I already rated. Netflix cares about predicting the rating of a movie that I have not yet rated. Okay. And let's talk about the credit card application. The bank doesn't care about whether you say yes or no to an applicant who they've already either denied or approved, and then you match. You say, oh, you approved that applicant? Well, I agree. Oh, you rejected that applicant? Well, I agree. Bank doesn't care about that. Bank wants to know what to do on a new applicant. Okay? So let's try again. What does it mean to have learned? Okay, and we can come back to the actual statement here. The result of learning is an approximation to f. Okay, so what it means to have learned is that g is approximately equal to f. And we've already said that we don't care about the data set. So that means that, we care about outside the data set. G is approximately equal to f for the next test input. Let's call that, just for the moment, let's call it x star. So that would be a way to quantify the fact that g is approximately equal to f for the context that's relevant to machine learning. It's true that if g is equal to f on the data set, then in some sense g is approximately equal to f. But we don't care about that. What we care about is that g is approximately equal to f for some unknown test input. Now, this in its entirety is the definition of learning, is what it means to learn in its entirety. Okay. So we can drop all this other rigmarole, okay, and just box this statement and we're done. So learning is the act of producing an approximation to the unknown target function f. I don't care how you do it. Okay, that's the definition of I have learned. Okay. And now what we've done is we've put that task of producing an approximation to f in a very specific context. What's the context? I'm going to give you some help in producing that approximation. What's the help I'm going to give you? I'm going to give you this data set. So you are tasked not with in some arbitrary, out of the ether way producing g. You're allowed to use the data set to produce g. But at the end of the day, the only thing I care about is that g is approximately f for the next time I need to make a decision. Okay. So that's the definition of learning. Okay. So let's put it in a box. The output of learning, so put an arrow here saying that this is the output, is g, which is approximately equal to f. In other words, g on some unknown test point, unknown as of now, unknown as of the time at which you have performed the learning, is, let's say, approximately equal to f of x star. Where approximately equal to depends on what the nature of the output is. If it's binary classification, then we want equals. So if this is yes, then this should be yes. If it's setting the credit limit, then approximately makes sense. So if the true credit limit is 10,000 and you said 9,800, that's pretty good. Okay. So when we define the learning problem, F is defined. It's unknown, but it's fixed and well defined. It exists. The data set is given to you. So, given. Fixed. The target function is fixed, but it's unknown. Okay. The goal is universal. You want to output an approximation to the unknown target function. It's fixed, but it's unknown. Okay. And so then the question is, how do we go from what's given, we can't change it, to the goal, in some way ensuring that we achieve learning. So this is what learning outputs. Okay, and now what I'm going to propose to you is a very simple way of accomplishing this task. It's very simple, but we don't lose any generality in how we're going to accomplish this task. Okay. So the first thing is, we're going to need some way of going from the data to the output. So let's call that the learning algorithm. A. Nice. Well, that's totally generic. There's nothing, there's no content to this statement. There's some magic that we're going to do that takes us from the data set to the learned final hypothesis G. By the way, this is called the final hypothesis. So it's a hypothesis about what is F. May or may not be right. Ideally, it's close. Okay. You can't argue with this. There's nothing to argue with. I'm doing some magic and I'm not telling you what the magic is. Okay. Later in the class, we will tell you what this magic could look like. Okay. But for the moment, I do something that converts the data set into my learned final hypothesis G. Okay. But what I can do in some senses is narrow down this A to a plausible type of learning algorithm, one which says the following. Okay. Says I'm going to define a hypothesis set. So I'm aiming to pull out a final hypothesis G. So let me define a hypothesis set. Let's call it script H. Okay, and what is this hypothesis set? It's a whole bunch of functions that live in the same space as F. Okay, so that map X to 1. So let's call that set of functions script H. And, just for convenience, I'll imagine that it's a listable set, but it may not be. Okay, and it consists of the hypotheses H1, H2, H3, and so on. Okay, so it's a set of hypotheses. Well, no big deal here. Okay, I defined a set of hypotheses H. And I am going to assume that this set of hypotheses is fixed ahead of time. What do I mean by ahead of time? Before you see the data. Okay, now you might wonder, whoa. How am I going to fix that hypothesis set? How do I know how to fix it? But we're not going to worry about that for the moment. For the moment, we're just setting up a very general framework. And I'm going to argue that it is without loss of generality. So I'm not telling you what to fix it to. I'm just saying it is fixed ahead of time, before you see the data. Okay. And what is the purpose of having this fixed hypothesis set? The purpose of having this fixed hypothesis set is your learning algorithm is going to be restricted. In what way is it going to be restricted? It's only allowed to pick as G one of the hypotheses that are in H. So this guy H is also feeding in to my learning algorithm A, and my learning algorithm A is forced, constrained to pick a hypothesis from H. But how it picks the hypothesis, we're not specifying. So there's some magic that we still need to specify. But what it does is, at the end of the day, produces one of the hypotheses in H for G. So in other words, G will ultimately belong to H. Okay. And now you're probably stepping back and saying, whoa, 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 whoa. Okay. You started off by saying, oh, this is going to be completely general unknown F of arbitrary complexity or whatever. Okay. And then you restrict me to fixing a hypothesis set before I see the data? So F is unknown. I haven't seen the data, so I don't know anything about my machine learning problem that I'm about to be asked to solve. And then you're asking me to fix a hypothesis set? Okay. So have we lost all generality here? Am I going to fix this hypothesis set to something special? No. So I'm still maintaining all generality. Okay. And to convince you of this, it's exactly because I haven't specified what this is. So, you know, if you want, go ahead and choose this H to be every possible hypothesis on Earth. So, one choice. H equals everything. Okay. This specific setup does not prevent that. Okay. So that is just to convince you that we have not lost any generality here. So this is a perfectly general framework in which you can produce a final hypothesis G. If you want, consider H to be everything. Everything you want. Okay, and then it's not a restriction at all, and then the algorithm, that's where all the magic goes on. The algorithm is going to pick one of those H's and produce it as G. No loss of generality. So this is a perfectly general paradigm. No downside, no loss of generality. But, and here's the big but, okay, it is, however, opening the door that if we carefully choose this H, we may be able to get a better G. Okay. So there's no downside because you can certainly implement this paradigm with the most general H on Earth. Okay. So there's no downside. But there is a possible upside if we can figure out somehow what's a better H to put in here. Okay. And a lot of the content of the theory that we will shortly start discussing after we define the learning problem more carefully and discuss whether or not it's feasible, a lot of the content of, you know, of being a good machine learner is figuring out what's the right H to put in here. Okay. But that doesn't detract anything from this general framework. Okay. This general framework is perfectly general. There's nothing lost here by saying that you had to fix a hypothesis set ahead of time. It turns out that even though there's nothing lost, the fact that you fixed this hypothesis set to H ahead of time, the fact that you fixed it ahead of time is going to make a lot of the theory go through. Okay, and then when we see that theory, it'll say that, you know, yes, it's great that you fixed it ahead of time because that made the theory go through. But also, when you did that, the theory is now going to start making recommendations for other H's other than this most general possible. Okay. In fact, it's not possible to learn with the most general, even though that's allowed in here, it's not possible to learn with the most general H. And the theory that we will discuss is going to precisely set limits on H. Okay. And, you know, what are those limits that it's going to set on H? Well, you know, what we're going to, okay, I lied a little bit. You know, you have to fix H ahead of time without knowing the data set, but you are allowed to know the number of data points you have. Okay. And so the theory will work for any fixed H. Okay. In particular, it'll also work for H being everything. But then the theory will say that, you know, and it'll still work if you know A, if you know N. Okay. Before fixing your hypothesis. And the theory will say that, you know, depending on the number of data points, there's a good way to choose H and there's a bad way to choose H. Okay. Now, the thing is that theory will fall apart if you looked at the data before you fixed your hypothesis set. So while there's no loss of generality here, there's going to be good practice, okay, in choosing H. And in order to allow that upside to realize, it is absolutely essential that that you fixed H ahead of time. Okay. So let's box this. Nice, beautiful flow chart. And I'm going to, simply state that this is the setup of the learning problem. Okay, so let me summarize. You have an unknown target function f. That target function is indirectly responsible, even though you don't directly have access to it. You may have access to it in some situations, or you may not, but for machine learning to be applicable, you have to have a set of examples, the data set, which represents the target function in action. Okay. So given this data set, we have to somehow produce a final hypothesis G, which approximates the target function f. Okay. And how we do that is very simple. There's some magic which is undisclosed yet, is as of now undisclosed magic, which is going to take the data set as input, okay, and produce this final hypothesis. So somehow this G is going to depend on the data, and the data depends on f, so indirectly G depends on f. Okay. G is good if it works on an unknown test point. Okay. And now we're going to restrict the workings of this algorithm in the following way, that this algorithm is going to have to, required to pick G from a fixed candidate set of hypotheses, which we call the hypothesis set. And let me just re-emphasize that having to fix this candidate set of hypotheses before you see the data is not a loss of generality. You can always pick it to be everything, every hypothesis, and then we're back in sort of this general framework where everything is pumped into the magic of A. So you can think of A as a two-step process. The algorithm starts by fixing a hypothesis set, then it gets the data, then it uses the data and its prefixed hypothesis set to produce G. Okay. It turns out there's a lot of upside to be gotten from fixing H, and we will discuss that. Okay, so that's all for today, and see you at the next lecture.